So let's apply all the expansions that we had just calculated to the differential equation and initial conditions. And so looking at the problem at the leading order, at order 1, we have this differential equation, a very simple differential equation, a second time derivative with respect to fast time, plus v0 tilde equal to 0. No forcing term and no damping here. This is the at leading order, since damping is very small, we have the undamped oscillation problem. Initial condition, displacement at time 0 is equal to 1 and the velocity is equal to 0. And so we can obtain the solution at this stage as the linear combination of cosine and sine functions with respect to the fast time times coefficients, which of course depend on the slow time tau 2. Slow time appears parametrically at this level, and of course, since we have these boundary initial conditions with time derivative, we calculate this time derivative, and so we can see that this is the function, this is the solution, and its time derivative. And when we apply these boundary conditions, we can deduce easily that these are the values that these coefficients a1 and a2, when tau 2 is equal to 0, they will need to satisfy these initial conditions in order to be able to compatible with the requirement of the problem. And so at this stage, we know that these functions, which are functions of slow time, have these initial conditions, and we have to find these slowly varying functions that multiply the cosine and sine terms. And we will see that this will happen at the next stage in the perturbation expansion. We will be able to find that. We consider the ODE at the next order, at order beta, and in writing that out, we're going to introduce a shorthand. So these coefficient functions that we have encountered before, we're going to need their derivative with respect to the slow time, and so we're going to use this shorthand that a1 dot represents the derivative of this coefficient function, which depends only on the slow time. So there's no ambiguity in this notation. This derivative with respect to slow time is simply referenced by putting a dot. All right? Okay. And so let's write the differential equation at this order. So v1 tilde is the correction to the undamped oscillation. So left-hand side is still the undamped problem here. But now on the right-hand side, we have terms that appear as corrections from both the multi-timescale expansion that we have introduced, and this term is coming from damping. This is the 2 beta, the first derivative of the solution with respect to time. When we move that to the other side, the displacement at order lower than the order on the left-hand side appears here naturally, and minus sign is simply coming from transferring from the left-hand side to the right-hand side. This term came up from the expansion of the second derivative, as we saw before. And so this entire right-hand side is calculable because we have the expression for v0 tilde that we had already obtained in terms of the sine and cosine multiplied by the slowly varying coefficients. And so we can substitute that, and so we have this expression. Each of these terms has two terms, so we can put them all together. And so then we can factor this out, factor multiplying sine of tau 1 and a factor multiplying cosine of tau 1. And so at this stage, we are reminded that this problem resembles what we had before when we were doing regular perturbation expansion, that we have these terms, sine tau 1 and cosine tau 1 are solutions of the left-hand side of this differential equation. They are solutions to the homogeneous differential equation. And so if we let such terms, which we call secular terms, be present, then they are exactly the ones that cause problem. They cause growth in time, which is proportional to time. But at this stage, we have arbitrary functions, a1 and a2, available to us, and therefore we can eliminate these secular terms. This freedom now we have, we can avoid the secular terms altogether by setting the coefficient of these secular terms exactly equal to 0. a1 dot plus a1 is equal to 0, and a2 dot plus a2 is equal to 0. We can set them like so, and so we can solve these. And so a1 is then given by this function and a2 is given by this function, and these coefficients can be found by the initial conditions expanded at order 1, which we saw before. And so a1 0, this coefficient is equal to 1, and a2 0 from the initial condition that we had before is equal to 0, and therefore this function vanishes altogether. It's just the a1 function that we have to treat, and therefore we can write that at leading order the solution accounting for now correction at order beta is given by this expression. The slow function is no longer arbitrary, it has been determined to be this exponential function, and this coefficient here is 1 times this cosine function. So we can interpret already that the solution now corresponds to oscillation at a frequency that has been chosen to make time non-dimensional, but amplitude of that oscillation decays slowly, exponentially on a time scale which is embedded in tau 2. So the rate of decay is beta, and so it's decaying slowly by that factor beta relative to this time scale tau 1. And so we'll have more to say about a more complete solution, but we already have made significant progress. You can see that this solution is already much more appealing than the solution we had before. And so now we need to proceed further. What we need to do is at order beta, so far we have not imposed the initial conditions, and so we have initial condition which corresponds to the displacement being equal to 1, and so correction to displacement is 0, and then the condition on the velocity, that velocity disturbance was 0 at time t equal to 0, and this sum is the correction at order beta to the velocity, and we have already satisfied the leading order velocity condition, and so correction must also be 0, so this sum must be equal to 0. And so if you look at it, this part of it is something we can calculate from the solution we already have, and therefore it gives us initial condition on dv1 tilde d tau 1, and so we can calculate that, and that's equal to 1. And so now we can complete this by recognizing that the equation for v1 tilde is actually become a homogeneous differential equation. Why? Because the secular terms that showed up, we chose the coefficients of those secular terms to be exactly equal to 0, and therefore and the terms on the right hand side were entirely secular, and so coefficients of all the secular terms have vanished, and so there are no terms on the right hand side anymore. So it's a homogeneous differential equation for v1 tilde, and its solution is therefore sum of the two homogeneous linearly independent solutions, and then using these initial conditions we can see this initial condition and that initial condition that the solution can be expressed in general in this form: sine of tau 1 times unknown function which depends slowly on time, capital B of tau 2, with this initial condition that B, capital B of 0 is equal to 1. And so this function B, capital B, needs to be found, but the form of the correction to this solution that we had at previous order is quite simple. This dependence is still to be found, and that is what we will turn to next. So the ODE at order beta square is written over here. So the left hand side is the spring mass oscillator system, and the terms on the right hand side, these two terms are associated with the multiple time scale expansion that we introduced, and this term is associated with damping. And now everything on the right hand side is already known because we have V0 has been calculated, and V1 we just proposed a form for V1, and so the homogeneous solution to V1 and V0, as has been found before, we substitute, and so we have these terms, and we can clean them up, and we see that once again we have a secular term showing up on the right hand side, the secular term multiplying cosine of tau 1. The terms have been put in the bracket here and involving the unknown function b. And so since we don't want the secular terms to show up, we choose the coefficient in the curly bracket here to be exactly equal to 0, which is an equation which we can solve. We have learned about solving such first order inhomogeneous equations. We can see that multiplying this equation by e to the tau 2 will turn the left-hand side into an exact derivative, and so we can write it like so. And so right-hand side, upon multiplication by e to the tau 2, will simply become 1/2. And so we can integrate that directly, and the constant of integration can be found by imposing this initial condition that b of 0 is equal to 1, which we had previously noted. And so incorporating that, the solution is going to be that the v1 tilde, its dependence on the fast and slow time, is given by this expression here, 1 plus tau 2 over 2 exponential of minus tau 2 times sine function. So it's an oscillation whose amplitude, if we plot this function as a slow function of tau 2, we'll see that this function is going to grow and then is going to decay, and so, but will never become unbounded. It's a well-bounded behavior. So now that we have found v1 tilde, we want to use the information to find the initial conditions for the next stage of expansion. And so the initial condition at expansion level beta square are these two conditions, but now we can calculate dv1 d tau 2 from this expression, and we can substitute that and find dv2 tilde d tau 1, and once we substitute this expression for this derivative carried out here, we can see that this whole thing, although this factor in the front is non-zero, is multiplied by sine of tau 1, and so when we put tau equal to 0, this whole thing vanishes, and so then the boundary condition at this stage for the derivative is that it is equal to 0. Of course, the function itself is also 0 for the second order expansion. And so now the ODE is again homogeneous because we made the secular terms vanish, and we have just noted these two boundary conditions, this and this boundary condition. And so the general solution to this homogeneous differential equation written in this form will need to satisfy these coefficients will need to satisfy these 0 initial conditions, that d is equal to 0 because the function at t equal to 0 is 0, and c must at 0 must be 0 because the slope vanishes, and so on. So at this stage we have unknown functions capital C and capital D, and we need to go to the next order in the expansion to find equations which determine capital C and capital D, and that is what we will do next. So to find these unknown functions, capital C and capital D, we have to go to next order as we had seen at lower order. And so the ODE at order beta cube is ODE of this form. Again, the structure is very similar to what we had at lower order. On the left-hand side, we have the same differential operator. On the right-hand side, we again have terms which we can evaluate because we have already evaluated v1 tilde and v2 tilde. So we can evaluate all of that right-hand side. And so it's important to do this algebra carefully and check it so that we can rearrange it in this form, and I made sure to do this a couple of times to make sure I have the same consistent result. And so we again have two secular terms involving sine of tau 1 and cosine of tau 1, which are both solutions to the homogeneous left-hand side operator. And so the coefficients multiplying these secular terms are shown here. And so in order to avoid these secular terms, we would put the coefficients in these curly brackets equal to 0. So the simpler of these, the second one involving C, setting this equal to 0 gives us an exponential solution with a coefficient C sub 0, which when we impose the initial condition that C at tau 2 equal to 0 is 0, gives us a trivial solution. So C, capital C function is equal to 0 identically, and so that vanishes altogether. And so a capital D function, which we do have to keep track of, arises from setting this equal to 0, and so moving this term over to the right hand side gives us this, and we can again identify that we can integrate this by using integrating factor, same integrating factor as we had used before, which gives us this solution with capital K as the constant of integration that arises by integrating once, which we can find by recalling that the initial condition d of 0 equals 0 needs to be posed, and so that gives capital K equal to 0. So finally we have the solution for this unknown function d of tau 2, d of the slow time, given in terms of this expression. So we have a polynomial, a quadratic polynomial, multiplying this exponential decay function. And again, its behavior is going to be smooth behavior. It starts at 0 because this function vanishes at 0, and it increases and then decays because of this exponential decay function. And so this process that we have applied so far can be applied at higher order as well. Now that the secular terms have vanished, again we have homogeneous differential equation for v3 tilde, and we have these initial conditions on v3 tilde, solution of this homogeneous differential equation, and we can solve it, and then its coefficients would be unknown functions of the slowly varying variable, and so those can be found at the next order and so on. And so we can keep on proceeding in this way so that we have a solution up to requisite order, up to requisite accuracy that we desire. And so we can now put all of these together to see what we have got. What is the nature of the solution we have obtained overall? So putting it all together, remember that the expression for the solution that we proposed was in this form, idea of successive approximations in terms of beta. Beta is the small parameter, and at each order the solution depends on the fast time as well as on the slow time. Tau 2 is the slow time, beta times tau 1, and tau 1 is simply the non-dimensional time that we have. And so this is the correction at order beta, correction at order beta square, and we have calculated up to here explicitly, and so we can recognize these expressions that we had previously obtained. We can put them all together, and then we can note that this exponential decay times cosine is something which repeats, and so we can reorder this by factoring that out. And so we have this decaying cosine oscillation, decay at a slow rate corresponding to the slow time. Its amplitude beyond this exponential decay also involves this damping parameter, and so that we have this. Actually, this is a mistake over there, so we can fix that because we factored that out, so they shouldn't be inside repeated again. And so the other term here involves this exponential decay of the sine oscillation, and so that's over here, and this coefficient is sitting here. And then if we went to this order, we would have a correction term here, and if we went to the next order after that, we will have a correction which will show up here, and so on. So they'll alternate back and forth. And so overall, the solution corresponds to a decaying cosine oscillation at leading order. Because of damping, this oscillation damps, but because of damping, there's also a phase shift, a slight phase difference relative to this cosine, and so therefore there is a cosine component, a sine component, and that sine component is small and also damps. And of course, there are higher order corrections that can be computed. And so we can compare this to the exact solution we had obtained before. So let's end by remembering that this method that we have learned about, method of multiple scales for dealing with problems involving small parameters, is a very powerful method which can be applied to nonlinear problems as well. It can be applied to higher order equations and so on. So it's a useful technique to learn.